Okay, so it's my great pleasure to welcome Dr. Alejandro Granados today. So Alejandro is a, a lecturer in surgical data science at the Surgical and Interventional Engineering Research Department at King's College London. He did his PhD in simulation and modeling for medicine and surgery at Imperial College London and has taken postdoctoral positions at Imperial, UCL, and King's. So Alejandro's goal of his research is to improve surgery from data perspective by increasing the predictive and prescriptive capabilities of patient-specific cases in the reduction of surgical complications using AI. So Alejandro.
Yeah. Thank you very much, and thank you everyone for being here. Yes, what I would like to share with you today in the next hour is the research that we've been doing at King's over the last 3 years. Very quickly, I'm originally from Mexico City. That's where I did my bachelor's in engineering in cybernetics, and I did an exchange in Canada towards the end of my degree. Then I moved to Imperial. That's where I met Corson. We did our PhDs together in a field related to simulation and modeling for surgery and medicine. And that then I did a couple of postdoctoral positions, initially at Imperial, then UCL at King's. And at King's is where I've been a lecturer for the last 3 years. We're strategically situated in London. Is just across the Parliament, as you can see on the top left side of the screen. That's St. Thomas's Hospital, and that's where our research group is. And one of the main and most recent contributions to the field is this MedTech Institute called the London Institute for Healthcare Engineering. Here we co-work with industry, and literally is just trying to make sure that our translation research can reach clinical practice. Specifically, we are part of the School of Biomedical Engineering and Imaging Science, led by Professor Oselat. And there are many areas of work that we've been working together there. But the one I would like to share some research is in surgical and interventional engineering. Our main lab is this mock operating room facilities that we have at St. Thomas's. Now, today, I'm going to focus on that work related to hopefully getting to a point of reducing surgical complications in patients. Now, the reality is that surgery is extremely complex, as you may know. And despite the numbers I'm showing you probably over 10 years ago, surgical interventions are many, increasingly. And then despite that increase in surgical interventions, we also have a huge gap of unmet surgical procedures. But the reality is that over 4 million people are dying within 30 days of surgery. And complications also result from both technical and non-technical skills, another type of errors. This is a situation due to many challenges. First, we have a poor understanding of really what's causing such complications. And this is mainly because surgery is systematically underreported. And most of the process entirely focuses on patient records, but over pretty much ignoring surgical data. And what is happening is that whatever we are proposing, mainly AI, to be tested in the operating room, is not reaching clinical trials. And the reality is that video is the most exploited modality in the operating room. More importantly, we have a situation where surgical data is literally not representative, it's not large. It's mostly single center and it's very, very limited. And there's no interoperability of devices in the operating room. And although AI brings opportunities, it's rarely used to understand what actually is leading to surgical outcomes. I like this figure, which I adapted from Wagner et al. This is literally what our standing point. Right? And of course, when we talked about surgical data, we are talking about that information that is available before surgery, during surgery, and after surgery. But strictly speaking, this is the aspect I would like to highlight today, right? That despite the research that we see today, and not many approaches are leading to this. And the work I'm showing you today, hopefully, is leading to that aspect. Now, the reality is that there are many ethical challenges, and this could be in the context of how AI could potentially be used in the operating group, mostly for decision making. That brings a lot of ethical questions. And then, of course, if we don't have representative data sets, then that's a huge limitation. Another aspect to look at it in terms of challenges is education and how we can improve practice. And as you know, explainability is quite important, but then reporting in a qualitative and quantitative way what's actually happening in the operating room is mandatory and would open new opportunities. If we see, for instance, what's happening in the field in terms of video and access to video, this is the most representative literature that I've found recently. And we would like to improve complications, but the reality is that there's a lot of concerns from the ethical point of view and privacy of the adoption of AI in relation to processing video. So this of course poses limitations for moving the field forward. And imagine how would that be if we would like to be interested in processing audio or views of the surgical team, etc. But today, what I would like to show you is 3 different research pillars that I've been working recently. And the way I stratify them is in 3. Those related to how can we perceive surgery holistically and not only on the endoscopic view. Also in terms of understanding surgical workflows, and moreover, to learn complex surgical tasks. And I stratify these 3 main areas of research across 3 different surgical interventions, mostly endoscopic, robotic-assisted, and interventional imaging in procedures. Let's start with perceiving surgery holistically. So I work very closely with neurosurgeons, and this is in the context of pituitary surgery. Here, surgeons insert small instruments through the nostrils to access the base of the skull that they drill. Then they get access to the brain in order to reach the pituitary gland. And this is because mostly there are tumors located in that area, and this is intervention related to those. And there are different types of complications here, from how you could access the brain, any leakage after finishing the surgery, and many others. In this context, there has been few contributions from the engineering side. Initially, we were interested in building a platform that could be used for recording multimodal data. So this platform is specifically designed so that the different modalities that could include audio, video, force sensor, robotic system could be synchronized and running in real time. But also on the right-hand side, that's an extension of that platform that is literally optimized for inference in the operating room, and especially when we liaise with robotic systems, and that's why we extended the ROS2 platform. What we also introduced is an annotation tool that can be used in real time, let's say in a room adjacent to the operating room. And here we can specify to some degree manual annotations to start curating data sets that, of course, eventually could be done by AI algorithms. But here it's an example in the context of neurosurgery where we can annotate all the phases that are occurring in real time, and then what's the skill that is given to the surgeons. And that means that we can score them, we can understand the workflow, but also an expert can be articulating what's happening in the operating room. And again, all these areas, our vision is to replace them with algorithms, but we need that data set to work with. In terms of inference, we have developed a ROS2 and GStreamer platform that is running in real time using Onyx. And here, what we are benefiting the most is we are programming in the language Rust. And we are getting to a point of using those cameras in the operating room running at 30 frames per second. Here is an example of how, for instance, YOLO is running inference and detecting objects with that. And then the experiments that we are running at the moment is how can we be more strategic, given that we have multiple modalities? Can we run them in a distributed fashion using edge computing, or in combination with more centralized and more powerful inference devices? To demonstrate what we have been doing in a mock operating room, this is just an illustration of the views, from endoscopic views to those cameras pointing to the surgeons, and we record depth, force sensing. We use gyroscopes in the wrist of the surgeons, and literally it's just curating a data set that we are doing research on at the moment. Some of the examples that I would like to highlight is with this data, we've been able to understand the dynamics of the surgical team, especially how they move and how they interact with each other. An example is building technology so that we can identify when and how frequent the exchange of tools are occurring from the assistant to the main surgeon. And this could be informing the development of automated robotics on how to develop such a systems to potentially replace the assistants. Another key area that we are looking into is in terms of ergonomics. Typically, because this is endoscopic, at some point when things get very complicated, they start leaning forward or taking very random positions. And so based on the kinematics of the body, what we are having is based on a straight posture, we can actually compute metrics that indicate how different from that straight position the surgeon is, and potentially understand what's actually happening. And that would, of course, help in avoiding musculoskeletal injuries. Some of the work also that we've been doing is in relation to audio. Here, one of my students developed audio and video system based on a foundation surgical VIT. And what is happening is that we are building a model that's processing video and audio in real time. And we linked that information to what the experts are actually mentioning about the performance in real time. So the task in this context is, can we detect when something is wrong, and given the comments of the expert? And this is the baby steps towards actually having an assistant in the operating room. So far, what we notice is that when we train a system entirely with audio, we have an overfit model that is not generalizing well on scene data. And then when we train only vision, it reaches a performance that is similar to that training with vision and audio. This is a very limited project in terms of data set, and as we continue iterating the data, we would extend it not only to classify errors, but also start generating those comments in real time for practitioners. Another area that we are working on is with federated learning in the context of surgical data. Here, we submitted this to MICA, and what we are suggesting and proposing is an integration between two main technologies. One, YOLO, and the second one is using Flower, which is one of the main software platforms for federated learning. And this integration would allow us to do experiments in terms of what strategies will be convenient when we are processing different clients, imagining that data would come from different hospitals. And without exchanging the data, what could be the main strategies of exchanging the weights of a model when we are fine-tuning existing models, in this case for object detection or other tasks. But one area that we are also investigating is how can we actually capture the human-robotic interaction element in terms of robotic skills training, and what would happen if we understand the learning curve of practitioners. In this context, what we are doing is putting April tags into existing robotic systems, and we've been doing experiments with the Da Vinci and Hugo robotic systems at Guy's Hospital on a phantom model. So what is happening is that we will be recruiting participants. You can see here in a Hugo robotic system, those markers of fiducials, and we are tracking that over time. And what we are finding is very interesting things so far. On the top hand side, we have very total novices coming to Guy's Hospital and doing robotic training on 3 different days. And what we are mapping is actually what's the movement, for instance, on the left side and on the right-hand side as given from those fiducials that are tracked over time. And the idea is that we can actually compute the volume of movement with this hand movement and how the hands are related to each other. Novices, for instance, they are very, hands are not synchronized at all. And we would like to measure how that relationship of hand dexterity and the workspace optimization can occur over time. Also, for instance, we've been mapping path length or the distance that the hands are moving independently for the dominant hand on the solid lines and on the dashed lines, the left hand. And how through different repetitions over time, those skills are changing for these participants. Again, we are running studies. So far, we've been recruiting up to 30 participants, and we see this moving on for understanding performance. Now, moving on to the second area of research in terms of understanding surgical workflows, I will fully concentrate on radical prostatectomy, which is robotic assisted. In this context, the patient with advanced prostate cancer undergoes surgery so that the surgeon would remove the prostate gland entirely from the patient. And the idea is that once this prostate is removed, you would put this end of the bladder to that of the sphincter so that there's no urinary incontinence. But there are many things occurring here. Let me illustrate that with this video. So this is one of the patients that we are processing. In translucency, we can see the prostate gland that is going to be removed. But alongside, you can see these structures in pink color. These are the neurovascular bundles. Research says that whenever they are resecting the prostate, if they are cutting part of the nerves or damaging, then patients end up with erectile dysfunction. And of course, that's very, very huge complication affecting quality of life of patients. And what is happening is that, as I mentioned earlier, the end of the bladder, which is at the top, should be stitched together with this sphincter so that there's no urinary incontinence after surgery. But of course, the patients undergo radical prostatectomy because this structure in green is a lesion that is expanding, and it could be cancer affecting other parts of the body. With that, we have started developing initially, because video is the most dominant modality, we started working on surgical face recognition. And if I define the problem, literally, we would like to propose a model that runs in real time. And at a given time, we would like to detect or classify what's the surgical phase that is occurring at the moment. By that, this is illustrated with the Collect80 dataset. That is the most common dataset in the field. And this is no more than a classification problem. So when we started this project, we developed what we call a long video transformer. And this is because we realized that most of the surgical understanding models were looking into very short timestamps. And whereas radical prostatectomy, for instance, it could last even 3 hours or longer. So we developed this model. And the way it works is, given a series of previous frames and what we are looking at in the screen as the current frame during surgery, is passed to a first stage model where we extract special features. And this is the ones in blue. Then the goal will be, given the data set and the image frames, we would like to classify whether that last frame is phase 1, phase 2, etc. So to do that, we extract special features from the first stage, and then we use those ones across a short and long transformer that when we put together, we would process further on using a global transformer in a multi-scale temporal manner. Once we extract these features, the last step will be to fusion both the short, the long, and the global embeddings of such models into a last layer, a linear layer that will be able to classify that phase. But also we run an auxiliary task where we can specify a Gaussian function to indicate what could be the phase transition. And that's what we propose. Then we realized that actually most of the problem in surgical videos is that the frames look very similar throughout time. So we thought, okay, what if we keep a track of what features, how they change over time? For instance, here the instruments move, then potentially there's some coagulation. They keep on moving and so on. So the idea was, what if we keep track of those things that occur, but we don't want to annotate anything manually? So that if we keep track of those things changing over time, potentially we can better identify those phase transitions. Now, what we did as having that as motivation, we started by looking to synthesize that temporal element of our model. So we rely on max pooling, which is very commonly used in CNNs. And here we are using it over time. So literally giving an embedding that has, let's say, 32 or 64 dimensions, we would like to try what's the maximum value over time. And we will be keeping that in a structure that is called key pooling. And if we keep track of what's the maximum value, potentially those are the points that the next one, whenever is getting a new maximum value or larger value, we will be indicating those changes over time. And this is what we call a key recorder module. That was our contribution to ICCV. So again, we've got our input, that's the video frames. We would like to classify the surgical phases. We extract those embeddings from a spatial model. And we use, again, a temporal model that will capture those spatial embeddings. But now, instead of working with short, long, global, all those elements that we proposed earlier, we actually remove all of them into this key recorder model. And as before, we use fusion to put them back together. Then we realized that each of these dimensions that we are keeping track over time, this, for instance, the first 5 dimensions of such a model across different videos, we realized that the model is actually learning a pattern across each dimension. And those are the things that are actually keeping track of changes over time. So when we evaluate such a model, we realize that given the ground truth on collect 80 and autolateral data sets, where we realize that at the time of publishing this and compared to other state-of-the-art models, actually will be improving that performance, as you can see in less artifacts and flickering on these exercises, on these data sets. Now, going back to radical prostatectomy. So we already train a model right now in 2 institutions, at King's and on the hospital San Rafael in Milan. And we are running a multi-institutional data set based on a clinical protocol that we extracted from with the help of surgeons. And here you can see an example of the ground truth, the lower row, and our predictions with SCID, the last model that I showed you. And actually, it's very fascinating. We are getting a performance of nearly 90% of accuracy. Now, surgeons argue that, okay, I know what's happening, what's the value of having a system telling me what's the phase that I'm actually performing. And it's completely agreeable. So far, face recognition is kind of the starting point to understand the workflow of surgery at a higher level. So we have done other areas of research. Here, for instance, I'm illustrating that what would happen if we don't only recognize the surgical phase that is occurring at the moment, but also anticipate giving a long horizon when these transitions would occur. The best way to see this is, for instance, looking at this figure. On the x-axis is the temporal element of surgery from start to end. And then on the y-axis is a long horizon of anticipation given the current time at 0. So what it's telling us is that, for instance, if we are, let's say at this point, let's say 15 minutes in the surgery, then in the next 5 minutes, we will notice a phase change. Then another one is coming up at 8 minutes, and so on. And of course, the closer to the end of the surgery, we would only recognize when the surgery is going to finish. And the figure at the top is actually our trained model using 2 different generative-based approaches. And looking at it, of course, it's not perfect, but it's giving us an indication that we can learn such a task, right? So we've been doing ablation studies, given a baseline of how these models could perform with different long horizons and across different generative models, mainly that using single pass predictions or autoregressive approaches. And we have developed a system that we can discuss with surgeons on how best to use this intraoperatively linked with a large language model to assist surgeons in real time. There are many elements that still are pending for investigation, though. Now, so far, we've been looking at how coarse surgery can be understood, but of course, we can move on to other areas of research where we can identify what are the actions. Apologies, the video cannot be shown. But here the idea is, can we predict those finer elements of surgery, whether they are picking a needle, whether they are cutting, whether they are doing a knot, etc. And with that, at this point, we realized that no one is looking at surgical outcomes. So we started making work towards that. What I would like to highlight in the context of radical prostatectomy is a meta-analysis that we did in terms of, for instance, what could be the benefit of using 3D models given to surgeons when they are actually having that endoscopic view when they do the surgeries. So the literature is telling us that 3D models benefit oncological outcomes. So that means that there's less cancer left behind. But the evidence is not conclusive, right? Whereas when we looked at continence and erectile dysfunction, literally there's no evidence that can prove that. What I'm showing you here is only in the context of 3D models, but just imagine how it could be the moment we started bringing AI models into the operating room. And this is what we would like to see in the future. To illustrate this study, we are using multi-parametric MRI to identify through AI the different anatomical parts of the prostate gland, as I showed you earlier on. And we generate both 3D models and 3D printed models that are given to the surgeon in the operating room. And the idea is that once the prostate is removed, we would like to see whether there was any change. So far, the study is telling us that there's indeed a benefit. So given a control group, given a control group, and whether there was whether there was cancer left behind or not, we can see that this rate maps that of clinical practice. That means that nearly 27% of patients end up having cancer left behind after surgery, which is really sad to see. But once I introduce the 3D virtual models and the 3D printed models, the reduction of those complications are really evident, that I found that even they have a statistical significance in this study. Now, linking back the videos, the stages, the steps, the actions, then with those complications in context, we started having some outputs in relation to gestures. Here we are looking into what's the effect of 3 main gestures as they are seen in the nerve sparing step where they are removing the prostate from patient. What's the effect of those gestures on surgical outcomes? And in this case, oncologically for now. And we realized that hot cut, which is literally when they apply energy to cut the tissue, is the variable that has the most effect on outcomes. The higher the hot cut used, the more complications to the patient. And what we would like to see this is now, given the data and the annotations that we are using, moving on to AI models that can understand that. Last, the third area of research is in the context of autonomous robotics. Here, I'm collaborating with a reader in neuroimaging. And for those that don't have the expertise in terms of stroke, patients having stroke, mostly because in the cerebral vasculature, there's a clot blocking the blood flow through the brain. And when they go through the cath lab to have that imaging, then you will realize that the fluoroscopy, or the contrast would flow everywhere, but it reaches a point that blood flow is not occurring. And that's where they realize that there's a clot blocking the blood flow. So the idea is to navigate through the vasculature of the patient from the femoral artery, as you can see it here, go through all the aortic arch, getting to the right common carotid artery to reach that area of the brain that the clot is staying, and then suck it and remove it. That's the goal of the intervention. And of course, the complications could be huge. Here, in the context of the longer it takes to treat it, the more complications are affecting patients. So therefore, we see a benefit on working on autonomous robotics, especially if we can do them remotely, because this is the time that is affecting the most, right? How to get to those centers that are specialized to do the treatment. So we started this work looking at reinforcement learning in the context of navigation on vasculature. And we realized that none of the approaches in the literature at the time were focusing on cerebral vasculature. And half of the studies were related to reinforcement learning. And of course, those are the most recent ones, which were 80% of those studies. So what we started doing, we configure our task given a simulation environment, here in the context of catheters and guide wires inserted into the vasculature of the patient based on SOFA. And a work that course has been done heavily in the past. And we linked that simulation environment to an agent that learns through a distribution through a policy to understand what would be the best actions given the state of the agent. And though that policy is linked, of course, to a reward function that we call a dense rewards function, and literally is how can we get to that goal of reaching the vasculature where the clot is in the brain. And our observation space at this moment is not image-based, it's rather state-based. And that means that we are tracking the position of the tip of the instrument, such as velocity, accelerations, and mapping that throughout time. And we see this work, of course, extended to image-based. So the action space for this autonomous robotics is how much we need to insert these devices. That will be the translational speed, and how much we need to twist them and rotate them. That will be related to rotational speed. And that's what the agent is learning to do. Now, initially, we capture data from experts, from demonstrators, using that simulator. And we did studies using only the catheter, and both the catheter and the guide wire. But also, we were proposing an inverse rewards function that we were learning from the actual data offline. Later on, we introduced a larger data set that we can actually train an agent using up to 10 cases and 2 for as on-scene test cases. And this is where we introduced now safety in the context of what are the forces that the tip of the instrument is applying on the vascular walls. You could see here, for instance, that those reward functions where we included that force element, we noticed that it was less forces on the wall of the vasculature. Let me show you one example. On the left-hand side, we have that reward function that literally is going from the blue point to the green point as a navigation task. And on the right-hand side is what we what will happen if we add the force component. And given this color map, you can easily see that there are less forces during that navigation. Something that is quite crucial when doing this intervention. What we realized also is that all the autonomous approaches proposed in the literature, they were all over the place. They all use different anatomical vasculature. They all use different agents. They all use different metrics, etc. So one of the work that we are going to present at IPCAI next month is that benchmarking across different state-of-the-art reinforcement learning methods. So we reported for one of the most common phantoms used in the field, what will be the performance across these 4 different reinforcement learning approaches. And we did it in actual vasculature. And we hope that that can be used by others in terms of better comparison and better benchmarking. The last piece of work that I would like to share with you is what we submitted to MICA this year. And this is in the context of a world model. You can see that there's so many challenges in training reinforcement learning agents, as you will need. They are very specific, they take a lot of time to train, and they don't generalize well to unseen tasks. So here, the main motivation is by understanding better the dynamics of an agent and that simulation environment, we can build a multitask model, a multi-agent model, where that task can be better, be more representative and translate better to unseen scenarios. The way we frame it is, given our task, we created different subtasks, and each of these is done by different agents. And what we demonstrated is by extending one of the main world models in the field, which is called TD-MPC2, we realized that even though it was much slower than state-of-the-art model, which is on the right-hand side, SAC, soft actor critic, we realized that it gives us higher performance as we do our experiments. And you will see it later here. So for instance, when we are getting to the right branches of the vasculature, we realize that even though the performance, in this case, success rate is low, it's actually much better than state of the art when a single agent is trying to do everything. And that's the work that we presented. We are very keen now to start moving on to mapping the complexity of the vascularity in patients. And you can see that it could be some cases where, for instance, the angles of the branches that are patients can be much more difficult to access, or in terms of tortuosity, whether there's any bending that will be affecting that navigation. And eventually, all those angles that are when the agents need to be reaching higher levels of the cerebral vasculature. But with this, what we are working at the moment is the sim to real element as we move closer to phantom models to demonstrate that this can be used in vitro before doing further tests on humans. To summarize, I would like to highlight that surgery is still a global challenge, and it's imperative to find better methodology to understand and reduce surgical complications. Here, I highlight 3 main areas of research where these complications could occur, and working very closely with surgeons, we are finding methodology moving on to see the benefits of data, as it has an inherent value to improve surgery. And moving away from video, still, of course, highly relying on that because that's the modality that surgeons rely on as the main surgical input. But not underestimating the value of others like audio for sensing and every other element that can appear in the operating room. And this will be beneficial to fully map surgery holistically from the technical and non-technical point of view. And of course, if by doing all this, we will lead to approaches where autonomy could be more reliable. And as you can see, there's a lot of scope for future work. And with that, I would like to thank you all, and I will be happy taking any questions you may have.
Thank you, Alejandro. Very interesting, very wide spectrum.
Yes, yeah, there's a lot of
projects.
Yeah.
Yeah, so regarding past one vascular one. So can you tell a bit more about like sim to real? So because this is obviously guided by fluoroscopy, where you have like very bad quality image with loads of noise. You can have like higher quality, but then you emit radiation, which of course you want to use as much as possible. So, so how approach this?
Yeah. So very
like in the phantom,
exactly,
like trying
to bring it
add
to
this problem.
Yeah. Absolutely. So right now the agents that we have trained are state-based. So that means that we are only tracking the tip of the instrument. So we rely on a scenario that is very not realistic as we move.
So you're taking the center line as a reference point,
exactly.
Then you get the geometry.
Exactly. Right. And we are moving now towards in vitro experimentation. But that means that, of course, we have a camera pointing to that phantom moment. We are taking the robot, and we have a robotic system, custom. And now we are pretty much meeting that publication in terms of how was the accuracy of those agents when deployed on the phantom moment. But again, it's very limited because we rely on a camera. The worst that can happen is that it cannot track the position of the tip of the instruments accurately. And how the sim to real aspect is how can we introduce noise so the models are more robust to that. Now, alongside, we are having students working on image-based reinforcement learning. That is baby steps, but that's very important as we move closer to the patient.
So basically got success rate of around 20-something% just with state-based. So simple, like difference between the tip and the center line.
Exactly.
Now this is using SOFA, so it's like a CPU kind of simulation.
That's we're using GPU. Actually, the agent is training the GPU, but the software is
simulation. So involve overheads and have some multiple environments, I think parallel or
what do you mean by that?
Yeah, they do like 16, 20 simulations at the same time. Or no, or just run a single.
Just runs.
So I guess this is level bottleneck.
Exactly. It takes long.
Potentially out.
Yeah.
So of course it's difficult to simulate the wire, catheter guide wire of the GPU because it's sequential solver, exactly like a realistic log model of that data is in place. But yeah, I think the way to go is to simulate like in a massively parallel fashion. Have hundreds of simulations like that. Also teaching learning running on each other.
And then the other element is how can we get closer to that clinical practice where actually we have contrast and like that of even quantum rather than keeping track over time because that's not really
because loads of radiologists, national radiologists, they just kill the figures where they reach like the outcome when they enter the vessel, so they don't have to use
radiation
basically.
Yeah.
So this
okay. The exact time I don't know. I will need to check with my student, but literally we're talking about days. Yeah. And this is
simple
for a single. Yes. And of course, the moment we have now 10, we're moving to 30 cases, but just imagine all the processing that we need to do, like having not only one patient, but also a wide range of cases to try. And the question is, even when it spends a long time for processing, because you have much more data, how can that be tailored to the patient that you see in Sano? That doesn't make sense.
Yeah, so that all the imaging, because then if you vision-based, can run hundreds and thousands of the simulations and the GPU, but the memory run out quite fast.
Yeah.
CNNs for each of the simulations that they were so it's really like this 80 gigs of RAM or they have the smell of
No, exactly. Very good. And another area that we're looking into is how can we optimize the replay buffer? to get those situations where we can see that there's least performance, where we can benefit in those rather than just doing the first data is straight and there's not much to it.
And you look at single instrument for them. Dual.
Yeah, but the way I see it is, now that we are moving in vitro, we faced so many challenges. Now the question is, how can we improve in vitro, even with state-based or even as we bring imaging? But it's a huge element of not just connect to the point. And I believe we will need better simulation from the imaging side to cope with that translation. Yeah, I know. That's what I was very keen on showing this. Yeah.
Specialist.
Absolutely. Yeah, I've got one student for that at the moment. But yes, we're trying to make progress, but that's yeah. If there's an expert willing to do that would be much faster.
And to get specialty systems that are not up to date, to be honest. But when you check the contrast, you can get this rotational kind of scan. So you can extract very good meshes and assume of the vasculature.
Clinically. What I understand is that once a patient is in the cath lab, the radiation that is applied to see is by plane, by planar. So you have one view and another one like that. But then there's no, you can rotate it, but I don't think that rotates while they apply the radiation.
The electrophysiology department. So you don't need to inject the lab, they just press the button on the chest and
okay,
all the way completely. Yeah.
That would be very interesting.
Nice and extract that potentially.
Yeah.
Models. I mean, not only for the meshes or something like, but also
as input to the
agency to be like
exactly
generate train the diffusion models, generate models.
Yeah. Because what I anticipate is that there should be prior knowledge of the anatomy that an agent works with, but then of course, state-based is kind of blindly navigating. But once the image comes to place, it's like you will need to pass those 2D or 3D representation of the contrast so that it will be shown by now. And that's what is missing.
Yeah.
Yeah, definitely. There's something. Yes. And most of the comments that we have gotten in relation to this is that vasculature doesn't inform. Is friction representative? The more we go into that route is either we train agents and make contributions on the AI side, or if we bring all the same elements from simulation, that it will take years to train.
Yes. So that's a common problem. Yeah. Not like there are not many groups that we can take and go for custom simulation development that they are paid for smart level. Okay, so are there any questions? Okay, so there are no questions. Thank you very much. Yeah, so very interesting.
Thank you.
Cheers.